Okay, folks, let's have a look at the wonderful world of circle theorems. Let's go. So what these essentially are angle rules for angles in circles. And there are a lot of them. So I think there's about 8 in total that you're meant to go into the GCSE knowing. So we're going to introduce them partly at a time. Okay. The first one we're going to talk about is this one here. The angle in a semicircle is always a right angle. So that means if we draw a semicircle and we draw a triangle inside that semicircle, then this angle here is always 90 degrees. So how could we use that? Well, have a go at these 4 questions with just that one fact. See what you come up with. We'll show the answers in 3, 2, 1. So for the first one, you'd stick in a right angle here. You'd then have 3 angles inside a triangle, which we could take away from 180, and we would get that x is 18 degrees. For the second one, you'd do the same thing. Right angles on both of them this time. So x would be 180 minus 28 minus 90, which would be 62. And y would be 180 minus 90 minus 44, would be 46 degrees. Right, this next one. Well, this isn't actually using the right angle. This is, however, quite good for introducing something which is radiuses. On circle theorems, this central point O, that's always your center of your circle, any line that comes from there and goes to the outside of the circle must be a radius. So that green line there is a radius, and that green line there is a radius as well. Now what does that mean? Well, all radiuses, obviously in the same circle, are the same length. So what type of triangle is this? This is an isosceles triangle. And so if we want to find x, we're just going to go 180, take away 98, which is 82, and then halve it. We're going to get our 41 degrees. Next question kind of puts both of these things together. So can you spot any isosceles triangles here? So we've got a radius, we've got a radius, we've got a radius. So we have 2 pairs of isosceles triangles here. So the first thing we could say is that z is just 22 because it's part of an isosceles triangle with the 22. X, well, we can use the fact that this is a right angle. So we just take 22 away from that and we'll get that x is 68. And then y, a couple of ways you could do it. Let's use the top isosceles triangle. If we know that x is 68, then we know this is 68 as well. And so y is 180, take away 2 lots of 68, which is 44 degrees. You could have done it by finding the angle in the other isosceles triangle though and taking it away from 180 because it's on a straight line. The second theorem that we're going to introduce is the one on the left here. The angle at the center is double the angle at the circumference. This is also sometimes known as the double angle theorem for fairly obvious reasons. So if we look at our diagram here, if we have this sort of arrowhead shape, then if there's an angle on the outside that's A, then double that is the angle on the inside. That's 2A. So just bearing that in mind, have a look at these 4 questions and unpause when you're ready. Go through in 3, 2, 1. Okay, so for the first one, we've got our double angle at the center, that's 40. We want to get our angle at the outside, so x is simply half of 140. It's 70 degrees. Second one, exactly the same thing. Even though it doesn't have that arrowhead shape, that is still definitely angle at the center is 194. So angle on the circumference will be half of that, will be 97 degrees. And this is even true for the next one. So this doesn't look anything like that sort of arrowhead shape, but we still have, let's highlight this, angle at the center, that's with those 2 red lines, and we have angle at the circumference. And because both of those come from the same initial chord, the rule still applies. So x here is just 87 divided by 2. It's just 43.5. Lastly, you can have something like this. It would be wrong to say x is half of 234. It's actually half of this angle here, so we'd have to take that away from 360 to get 126. And then x is 126 divided by 2. X is 63 degrees. Okay, let's keep going. So let's go back to that first rule, that the angle in a semicircle is always a right angle. Let's see if you can apply that to these questions. Slightly trickier now. Pause the video, have a go, and we'll unpause in 3, 2, 1. Okay, so the first one is going to be about isosceles triangles, because you've got practically 4 of them here. Yeah, you've got 3, haven't you? Because we've got the same lengths here, and here, and here, and here, because they're all radiuses. So we can start fairly simply by saying A is 22 degrees. We can then find the missing angle here by taking away 180, take away 2 lots of 22s, take away 44 is 136. We can find 136 angle at the center, and we can say that C is 136 as well. Reason for that is it's what we call an opposite angle. Those are on opposite sides from each other. Okay, so what about B and D? So let's just rub off that 136 for a second. So we know that A is 22. We also know that because this is a semicircle situation, that is a right angle. And so this is 68 on the other side, because they've got to add up, obviously, to 90. And that will tell us that B is 68 degrees as well, because it's, again, an isosceles triangle. So we have a value for B, we have a value for C, and we have a value for A. So we just need to find D, and D is going to be using another isosceles triangle. D and the other green angle over here will be the same. So we'd have to go 180 minus 136 is 44, divided by 2, we'll get D is 22 degrees again. Cool. Okay, what about the second question? So just to run through them quickly, A is 21 because it's isosceles, B is 138 because it's in the triangle, E is 69 because it's on a right angle with 21, C is 42 because it's on a straight line with B, and then this very last one we've got another isosceles triangle here, so E and D must be the same. D is 69 degrees as well. Okay, what about the third one? Well, for the third one, we know we've got a right angle here. We also know that the other two angles have to add up to 90. So we can simply say that 3x equals 90, and so our solution would be that x is 30 degrees. So that's a 30, 60, 90 triangle. And then the last one is actually asking you to find a side length. So again, we can put in our right angle, and we can recognize this as a Pythagoras question. So 10 squared is 8 squared plus x squared. So we need to subtract that 8 squared to get our x squared, which is 36. And then square root that to get x is the square root of 36, which is 6 centimeters. Okay, let's keep going. Okay, so let's go back to the double angle theorem again. 4 questions, varying difficulty. See how you do. We'll unpause in 3, 2, 1. Okay, so for the first one, we're going to find a 44 degree angle. No, sorry, that's not true. A 68 degree angle here, because that's a double angle, and we want to halve for the value at the circumference. And so x is on a straight line with that. We'll take away this 68, and we'll get that x is 112 degrees. For the second one, we have an isosceles triangle, so we have a 22 degrees here. That means that the other angle as part of that triangle would be 180 minus 44 would be 136. I feel like we've seen that value before. And so if we want to get x, we can do the same sort of thing. X is going to be half of that 136, 68 degrees. What about the next one? Well, we know that x is going to be double this angle here. So what we kind of need to do is to work both of those angles out. And what we have here is yet another set of isosceles triangles to think about. They've all got radiuses. So we can definitely put a 34 here, we can put a 27 here, and so x at the center will be 2 times 27 add 34, will be 2 lots of 61. So x is 122 degrees. And then for the very last one, we're going to use double angle again, obviously. The angle at the center is double the angle at the outside. So 4x add 40, that's the angle at the center, is double the angle at the outside. So this is a linear equation. We would expand our brackets, we would collect our terms, we would find that x is equal to 30. And if we wanted to find the angles themselves, we could sub them in and get that that's 160 and 80. We could check that that works. Okay, so let's introduce another couple of circle theorems. First one we're going to use is the one on the left-hand side here. It says that angles from the same arc and the same segment are equal, and it's also sometimes called the same segment theorem. But what you're essentially looking for is this bow tie shape, or fish shape, or whatever you want to think about it. The angles at the top are the same, the angles at the base are the same. Okay, so looking at this first question, we can kind of see that we're going to use this bow tie to start with. We can see that B is literally just 37, and we can do the same sort of thing with this combo, and we can get that A is 37 as well. Simple as that. For the next one, we can start off and just say that X is the same as 52. So you're just looking for that shape, basically. What about the next one? Well, we can certainly construct one that involves A for 47. And then B. So B is actually a double angle theorem. If we look at this arrowhead shape here, we can see that B is the angle at the center and 47 is the angle at the circumference. So B would just be 47 times 2, would be 94 degrees. And then for the very last one, we can see that we've got a triangle in a semicircle, so it's bringing in the other rule that we've already looked at. And we know that this is a right angle here. So if we could find out this angle, we could find out x by taking that away from 180. And we can find out that angle because we've got, again, a little bow tie shape there. So 35 degrees goes over here. And so x is just going to be 180, take away 90, take away 35. It's going to be 55 degrees. Okay. So the other theorem we're introducing here is the cyclic quadrilateral theorem. And that is that if you have a quadrilateral, a cyclic quadrilateral, it just means all of the corners of the shape are on the outside of the circle. If you have that, then opposite sides, like B and D here, add up to 180. And the same is true for A and C. So, at its most basic, if we look at this first example, we can find x by simply doing 180 minus 71. We can find y by doing 180 minus 40, because they are opposite sides of a cyclic quadrilateral. What about for the second one? Well, opposites. So x is 180 minus 85, which is 95 degrees. And then x and y are on a straight line together. So y would be 180 minus 95 degrees. It would be 85. What about the next one? Well, we've actually got some parallel lines here. So we're going to use alternate angles. Y is 75 degrees because it's on a Z with that 75 degrees. What else could we do? Once we've got Y, well, we can get Z because they're opposite sides of a cyclic quadrilateral. So Z is 105 degrees. And then how do we get X? So X is going to be opposite to this angle here. So we need to work out what that is. And that's just on a straight line with 75. So we can work out that's 105. And so x is 180 minus 105, which is 75 degrees. Okay, and the last one looks like it's going to bring in some circle theorems, some double angle theorems rather. We've certainly got our arrowhead here, so x is just going to be double 36. Well, y is on a cyclic quadrilateral with that 36, so we just need to take away the 36 to get that y is 144 degrees. Okay. So here's a couple slightly more advanced same segment theorem questions. Have a go and unpause when you're ready. Put the answers up in 3, 2, okay. So first off, we've got a 25 over here because they are same segment. We've got straight lines here, so we know that this is 96 because it adds up to 180 with the 84. And so x is just in a triangle, it's going to be 180 minus 96 minus 25, which will give you 59 degrees. For the second one, we want to use these parallel lines here. So we want to use the fact that z and this will be the same because they form our alternate z. And then we can use same segment to say, well, that is actually 40 degrees. So x is 40. For the very last one, we'll use same segment to get that this angle here is 10. We'll then use, so it might be tempting to use like a double angle here, but that 25 is not at the circumference, so we can't do that. So we're actually just going to use the fact that this is one big triangle here, and so x is just 180, take away 10, take away 25. It's going to give you 145 degrees. If we know that x is 145, then we know that this is 35 degrees because it's on a straight line. And so y would just be 180 minus 10 minus 35 would be 135 degrees. Cool. So same thing as before. Here's some awkward cyclic quadrilateral questions. Have a go. Unpause when you're ready. And I'm going to crack on in 3, 2, 1. Okay, so cyclic quadrilateral wise, this would be 80 over here. It's opposite 100. And this would be 110 because it's opposite the 70. I can then use straight lines to say that this is 70 degrees. It's on a straight line with 110. This is 80. It's on a straight line with the 100. And so these three things together must make up 180 because you've got a little triangle here. So x is 180 minus 150. It's going to give you 30 degrees. For the second one, we know that opposites add up to 180. So we know that 5x minus 12 plus 2x plus 45 must equal 180. And that is a little bit of algebra that we can solve. So 7x plus 33 is 180. We can take away the 33. And we can divide by 7 and get that x is 21. And then we can fill it in what that would actually be. So 5 times 21 minus 12 would give you 93 degrees, and 2 times 21 plus 45 will give you 87, and they do add up to 180, so we know we've not made too much of a mistake. Lastly, y in that same question would be 180 take away 87 because it's on a straight line. With that 87 would be 93 degrees. And then the last one is a very fun question because it's a simultaneous equation. Opposite sides add up to 180, we know that. So if we add up these two, we'll get x plus 45y is equal to 180. And if we add up the sides, we'll get 3x minus 45y is equal to 180. Now, that's a nice simultaneous equation because we can add it together straight away and say that 4x is equal to 360. And so x is equal to 90. We can then sub that back into one of the other ones and say, okay, so 90 plus 45y is equal to 180. So 45y is 90, so y is 2. And we could finally go back in and fill in the angles and make sure they work. We know x is 90. We know 2 times x is 180 minus 45y, so minus 90 is also 90. So we've got two right angles there. We know 13y is 26 because that's 13 times 2, and we know x plus 32y is 154. Yeah, so opposites do still add up to 180. I think the phrase not drawn accurately describes that question though. And then finally, we have the last batch of circle theorems. So we have tangents meet radiuses at right angles. Remember, tangent is a line that does not touch a circle. If we draw two tangents from a single point, then they're the same length. That's not going to come in too much, but we will hopefully make some use of it. And lastly, we've got this alternate segment theorem, which we'll get to in a second. So for our first example here, we would simply see a tangent, a radius, put in a right angle. And so x is 180 minus 90 minus 68, 22 degrees. For the second one, we would see a tangent, we'd put in a right angle, and then we know that 180 minus 90 is the 3x that remain, is the x plus 2x. So we can divide by 3 and then get x is 30, so that's a 30, 60, 90 triangle. And lastly, for this x here, we know tangent and angle meet at right angles, tangent and radius meet at right angles, and then x is part of a kite, it's part of a quadrilateral. Quadrilaterals add up to 360. So if we take away the three sides that we know, we'll get the one that we don't, which is x, which is 165 degrees. Okay, so let's carry on and try and use a little bit more of these tangents. So the first one, we can put in right angles here and here. We can use the fact that angles have to add up to 360 in a quadrilateral. So we can take away the 180 plus 23, you can take away the 203, we can get this as 157 degrees there. And so x is on a point with the 157, so if we take that away, we'll get that x is 203 degrees. What about the next one? It's another missing side, it's another right angle, it's another Pythagoras question. So x squared is 12 squared plus 5 squared, which is 169, and so x is the square root of that, is just 13 centimeters. And then last one, similar job, right angle, triangle. So we can say that 30 squared minus 20 squared equals x squared. So that's 900, take 400 is x squared, which is 500. And so x is the square root of 500, which would mean it's about 22.4 centimeters. Cool. So alternate segment to go. So alternate segment is traditionally thought of as the toughest of the theorems. I think it's because it's difficult to spot. What you're essentially looking for is what we'll say a cyclic triangle. So a triangle that touches the corners of the circle that's based on a tangent. And if we have that, then the bottom right of that shape is equal to the top left, and the bottom left is equal to the top right. So you can see those two blue sides are the same, and those two red sides are the same. So at its most basic, you get a question like we've got here, where x simply goes with the 65 degrees, where y goes with the 63 degrees, and where z is just on a straight line with 63 and 65. So we take those away, and we get that it is 52 degrees. Okay, let's step it up slightly. So we can certainly tell on this first equation that x is 80 because it's on an alternate segment with it. What else can we say? Well, we've got a isosceles triangle here. So z is the same as this angle over there. And then we've also got a tangent and a radius. So we know that this is overall a right angle. This means that z is going to be 90 minus 80. It's going to be just 10 degrees. And then we can use the isosceles triangle and say that y is 180 minus 10 is 160 degrees. Okay, what about this last one? Kind of a bit of everything. We don't have any tangents to radiuses, but we do have a cyclic triangle, so we can use alternate segments. So we can say 35 goes here, and then what could we do? Well, we could use the fact it's parallel lines, can't we? So we've got an alternate shape here. We've got a z. That means that's 35. And then what? Well, we've also got a triangle. So we can say 35 and 180. If we put these two together, have to add up to 180 with this shape here. So that's 65. And then we should be good. So yeah, now we can use cyclic quadrilateral
to say that x is 180 minus 65, so that's 115. And once we know that x is 65, we've got a triangle with y in it, so we can say that y is equal to 180 minus 65 minus 35, which is 80 degrees. So you can see that all the circle theorems start to mix together in terms of what's being tested. And the next thing to do is to look at that sort of proof. But that's for another video. Cheers!